maybe I can already start a few words about it.
Yeah, sure.
Let's look at. So this idea of the observability function is not new. This is something that SIS, I think SIS is online today, that SIS has developed a long time ago, and we wanted to apply this technique to our BRAMS network. So in short, what is the observability function? So we will apply to forward scattering. So basically, radio observation, so the transmitter and receiver, which are not at the same locations, and we study the reflections on the meteor trails produced behind the object. So at the receiver, we receive a lot of so-called radio meteor echoes. But the raw meteor waves that we observe, for example, during a meteor shower, it's not exactly the real activity of the meteor shower, because I will show you it depends on a number of parameters. So we would like to find somehow the real or something closer to the real activity of the meteor shower. And one way to do this is to use this observability function. So as I said, this is mostly based on the work of SIS, published in 1997. And now a few words about our network, the BRAMS network, Belgian radio meteor stations. Antonio has already presented you a little bit about the network. So you know we have a dedicated transmitter here. Antonio already talked about that. We have currently 44 active receiving stations, all the dots here. And we are using the same material. So one vertically oriented 3-element Yagi antenna. And most of the recent stations are actually using Raspberry Pi and LSP2 digital receiver. So I would like to point it out, something that is actually related to Christoph. We have this box there, which includes, it's very compact, and it includes digital receivers and Raspberry Pi. So we are doing this. And next year, actually, at the ANC in Belgium, you will be able to have a live demonstration. This is what the BRAMS data look like in the raw data that Antonio mentioned. And indeed, as Antonio has explained, usually we look at spectrograms, so which is already we already analyzed these raw data, and we present them as 5 minutes durations, 200 Hertz. And you see here a very typical kind of boring spectrograms with just the direct signal at 1000 Hertz here, the horizontal signal, airplanes, as already mentioned by Chris and Antonio, and a lot of underdense meteor echoes, the vertical sign. During meteor showers, the story is different because meteor showers, there are bigger particles which produce more ionization, which means a longer duration over dense meteor echoes. So we have these complex shapes all over the images, which add on top of the sporadic background, which are mostly underdense. But of course, during meteor showers, you have also underdense meteor echoes. So here as mentioned also by Antonio, we rely for now 6 years on the radio meteor zoo to study the activity of the meteor showers. So people count for us, and we take that into account, and then we produce these curves that you've seen maybe in the previous, usually presented by SIS. This is, for example, the activity of the Geminids in 2008 from our station in Humain. And what you see is a double peak here, which is not real because, of course, there was one big peak of activity, but this is due to the fact that the radiant here is, this is the elevation of the radiant of the Geminids. And you see that, of course, when the radiant is really low on the horizon or even below the horizon, the activity drops to 0, obviously. But also, this curve is modulated by the position of the radiant. And this is something that the observability function should take into account. So what we see here is the raw rates of meteor showers observed. What we would like is the real activity. So what is important is the fact that most of the meteor echoes that we record follow the specularity condition. This is exemplified here. So you have a transmitter here and 2 receiving stations and 1 meteoroid path. What does that mean? It means that the reflection that we see, so the meteor echo that we detect, the power mostly comes from 1 point. This is the specular reflection point here. So for 2 different stations, we'll have 2 different reflection points. And the position of this reflection point, we can mathematically find it as the point where, on the trajectory that is tangential to an ellipsoid, that where the transmitter and receiver are the 40. Now that has an implication because if this reflection point is too low, so it's not in the meteor zone, so let's say between 85 and 105 kilometers, something like that, if it's too low or too high, the station will not detect it. So that means that we are not able with one station to detect all the meteorites seen in the surroundings. So the observability function should take that into account. So there is the geometrical part. This is explained here. This is the trail. You have the trail is in general inclined to this plane. This is the propagation plane of the radio wave going from the transmitter to the reflection point and back to the transmitter. Okay, when you do the math, and I'm not going to do it here, you obtain an equation. It's explained here, but I don't have time to go into the details. But when you do the math, which is did in 97, you obtain at a given altitude, you obtain a relation between x0 and y0. What are these things? These are the coordinates of the reflection point. So that means at a given altitude, at a given time, so when the radiant is in a given position, you obtain a curve at an altitude that gives the potential position of the reflection point. So if something is happening there, you will be able to detect it. If it's not there, you will not. So knowing that, you can obtain, this is now in the horizontal plane at 3 different altitudes and for a given location. So UMA is here and our transmitter is there. So 50 kilometers, that's a distance, 3 different altitudes, and we look for a radiant located in a specific direction, so azimuth, elevations, and angle given here. And what you see transmitter and receiver here, these are the theoretical position curves. So if a reflection point is somewhere on these curves, it will be detected by the station. So basically, one thing we've done compared to CIS in 97 is that we are now, because the computation means are much better than 25 years ago. So of course we can produce these curves for many altitudes. And what we see here is that it doesn't change so much with altitude. Here we have 90, 100, and 110 kilometers. So now we can just integrate over altitude with steps of 5 kilometers. So instead of having just one curve in a horizontal plane, we have some kind of curve, 3-dimensional curve that we have done. Now there is a second part, the sensitivity part, because all these points, if something is happening there, you will be able to detect it. If, of course, the signal is strong enough. So that means if I take, for example, this underlens meteorical, and I plot it not in a spectrogram, but as a function, power or amplitude in this case, as function of time. So here we separate with frequency, power versus frequencies there as well. Here we have all the frequencies, it's the total amplitude versus time. So here we have kind of underlens meteor echoes, and basically the amplitude, the maximum amplitude of the echo must be above some threshold, depending on the local noise at the station. And of course we have now, we have a way, basically the noise is somewhere over there. It's the blue that you see in the spectrogram. Now comes the tricky part. So how can we look at this value of the maximum amplitude? Now for underdense meteor echoes, there is this complex formula, but still analytical. Sorry. So I put it here again, and without too many details, the denominator there is the geometrical part. So because we have found all the locations, the potential locations, we know all these parameters, so we can compute them. Another thing in the denominator, I'm not going to look into all the details, but one of the things, many things that appear on the numerator are technical parameters, I would say, like the power that we transmit, the wavelength, etc., and the gains of the antenna. And again, for the gains of the antenna, for the receiving antennas, we are always using a 3-element Yagi antenna, so we know we can compute theoretically the pattern, and we have done that here, so we can use these values as a function of azimuth and the elevation. And for the transmitter, we have measured it in situ, so using helium filled balloon with a platform that you can see here, which is related to 2 short dipoles that you see here. So we flew at 10 meters above the transmitter here, 10 meters in the horizontal plane, and we measured the total power. So here There was also webcam, so you see the transmitter from above, the two dipoles here, orthogonal dipoles, and these are the ones from the payload. So we have all the data or the measurements that we took into account in the computation of the observability function. So now if I look again at the complex formula, basically it's not completely true, but nearly, the maximum amplitude that we can detect is related somehow to the ionization. So we need a minimum value of the ionization at that point, all along the points that we have computed, to be detected at the receiving station. So that puts a minimum value on the mass. And of course, in a meteor showers, we know that the distribution of mass particles is something that follows more or less a power law with an index S. This is called the mass index. Now, of course, we don't know the mass index, or we can use it from previous measurements from the previous years, but that's not the best way to do it. So what we plan to do is to calculate it from the, that's a little bit more technical, but from the cumulative distribution function of meteoric amplitude. So that's something we will do soon. But of course, knowing this value of S, now we can put a minimum value of alpha, and then we can compute the observability function. So basically, to summarize, we haven't done it yet fully, but we can calculate now the observability function for a given pair of the transmitter and any station of our BRAMS network at a given time. So that means for a given position of the radiant of the meteor shower. And we can compute the observability function here given as a polar plot. So unfortunately, the curve I got from the student was not very clear, so I don't show it here, but to give you an example, this is what Pavel Zigo did in 2008 for the Lecce modular system. So this is the value of the observability function at a given time as a function of, sorry, no, not at a given time. This is as a function of the zenithal distance and azimuth of the radiant, and it's normalized in this case. So we would like to do something similar. So one thing we can do is take two stations. So for example, UNA and Observability, because we have the counts from the radiometer zoo. So we have the raw activity of the meteor shower, of several meteor showers actually. And of course, these stations are different distances. They have different sensitivities depending on the localness, blah, 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 and slightly different geometry. So we can calculate the observability function at a given time, correct by the observability function, and we should find two values that are consistent with each other. One last limitation that I see here, of course, is that the sensitivity bar assumes in this equation underdense meteor echoes, while we know that during meteor showers there is a non-negligible part of the echoes that are not underdense. So maybe we could use other formulas. And I stop here. Thank you.